So in this video, we're going to introduce a super important topic, one that will come up again and again in the class. And the topic is this. Given a geometric object of some sort, and in this case we're looking at a curve sitting in two-dimensional space, but this can be applied more broadly as we'll see, can we find vectors that are tangent to, and can we find vectors that are normal to that given geometric object? And so in this case, maybe first of all I should say normal is going to be sort of a word that's synonymous with perpendicular, right? So I'm looking for vectors that are tangent to a given curve and vectors that are perpendicular to a given curve. And so just to see this schematically, or just to see this pictorially, here's a nice curve x of t, nice parametrized curve. And so what we'll be interested in are finding vectors that are tangent to this given vector, so they're tangent to the curve, and vectors that are perpendicular to the given curve. And we'll be interested in making sure that we can find such vectors at any given point on the curve. Right? While we're at it, we're also interested in making sure that these vectors have unit length as a form of normalization or standardization. Right? So what we'll see is that we can do this, that the tangent vector will typically be denoted with a t. Right? So that will be our tangent vector. And our normal vector, at least for curves in two-dimensional space, will be denoted with the letter u. So we have our unit tangent vector and our unit normal vector. And we'll see that we can compute these at any given point on the curve. OK, now let's start with the tangent vector, which will be a quick consequence of some material that we discussed previously. So recall, for any given curve x of t, we have the velocity vector, which is just x prime of t, and that velocity vector is always going to be tangent to x of t. Right? This is something that we discussed earlier. So the velocity vector will be tangent to x of t. And then we also had the speed of the parametrized curve, which was just the absolute value, or I should say the norm of x prime of t, right? But of course, this is a vector. This is the length of that vector, right? And I'll just sort of be really explicit here. This is the length of capital X prime, right? And so if we have a vector and we have its given length, we can perform scalar multiplication, or really in this case scalar division, to stretch or shrink that given vector to create a new vector pointing in the same direction of the length we want. Right? So in this case, we have capital X prime is a tangent vector. If I divide by its length, right, that means I'm stretching it down, shrinking it down by a factor of its length, what I'll get is a new vector of unit length, of length equal to 1, pointing in the exact same direction, and so still lying tangent to the curve. So in fact, this capital X prime divided by the norm of x prime will be a tangent vector. It will be of unit length, and so it is our unit tangent vector, which we said before we will denote using a capital T. All right. Love it. So here's an example, right? We're going to take the parametrized curve x of t equals t comma t squared for t values between -1 and 1. This just traces out the curve given by a parabola, right? Its locus is the standard parabola, y equals x squared, between -1 and 1. And so if we go to compute the tangent vector, I should say the velocity vector, and then the speed, what we'll see is that capital X prime, right? Well, that's just the derivative of t, which is 1, the derivative of t squared, which is 2t. And then the norm of this will be the square root of it dotted with itself, right? And so that will become the square root of 1 squared plus 2t squared, right? I should say 2t times 2t, so actually 4t squared. And so we get this as our speed at any given time. And now notice this will actually make certain vectors or certain points on the curve move faster than other points on the curve, which makes total sense, right? So if I were to graph some of these at time 0, right, our capital X of t would just be the vector 1, 0. So that's this vector right here. And that has total length 1, right? So at this moment in time, our curve is being traced out with speed 1. Perfect. If I were to choose a different time, let's say time 1/2, well, then I'm right here. My tangent vector, my velocity vector would be 1, 1. And that vector will actually be a little bit longer than this vector. And so its speed will actually be a little bit greater, right? It'll be the square root of 2. Right? And so our particle tracing out this curve is moving faster at this time than it is at this time. But if I want to create a standard function for the unit tangent vector, right, what I could do is I could take, for my capital T, I could just take my x prime divided by the norm of x prime, and what I would end up with is a vector that looks like this. I'll write the scalar multiple out front. So it's really 1 over the square root of 1 plus 4t squared times the vector 1, 2t. Right? And so what this has done is it's taking all these different tangent vectors and scaling them up or down to have unit length. So this vector would remain unchanged, that still has unit length, but this vector here would be shrunk a little bit. Right? So both of these vectors would now have the exact same length. And similarly, we could plot many other vectors of tangent C, many other tangent vectors of unit length on this curve. They would all be calculated using this expression. Okay, so there's an important question that we should now address, right? And this important question is what happens under a reparameterization of a curve? And sort of pausing for a second, right? If I reparameterize this curve in a different way, right? If I sped it up or slowed it down or what have you, that would change my speed of my curve. That would change my norm of x prime of t. But there's a hope, at least, that this wouldn't change the unit tangent vector, right? Because the unit tangent vector should always just be tangent to the curve. It should always have unit length. This seems more a property of the underlying curve itself, the locus, than it does the parameterization. And so, at least at first glance, it seems like reparameterizing this curve should not change the unit tangent vector. Right? So let's see what happens here. As a reminder, a reparameterization of capital X would be what we get if we take capital X and then plug in a function of t. Whoops, we plug in a function of t. And so we'll represent this with this Greek letter xi of t. So xi of t is our reparameterization of x. And now my question is, how does the unit tangent vector of xi relate to the unit tangent vector of x? And are they, in fact, the same as we're sort of hoping that they will be? All right. Well, let's compute, right? The way that we compute the unit tangent vector of xi is to take its derivative and then divide by the norm of its derivative. And so let's do both of those steps. Okay, so the first thing we have to do is we have to take the derivative of this. So we would get xi prime, right? And so to do that, we have to take the derivative of both sides of this equation. Taking the derivative of this side will require the chain rule. And so what we'll get is going to be an x prime of f of t, but then by the chain rule, this is times the derivative of f, so times f prime of t. And so we have that extra chain rule step there. Now, if we go to calculate the norm of this, we'd get xi, right? The norm of xi of t like this is just the speed of the reparameterization. Well, that is going to equal the norm of this whole thing right? So far, so good. But this piece right here, this f prime, that's just a scalar multiple, right? That's a scalar multiple that's rescaling the vector capital X prime. And so this can actually be factored out of this modulus. We have to introduce an absolute value sign. So this is really nothing more than the norm of x prime of f of t times, go a little bit off screen here, times the absolute value of f prime. Okay, and hopefully that all makes it into the frame. Perfect. So now, to calculate the unit tangent vector for xi, what we need to do is we need to take the velocity vector and then divide by its length. Okay, so on the left-hand side, right, so our unit tangent vector will just be xi divided by the length of xi. I'm just going to not write the t's, but we know that this is dependent on time t. And I'm sorry, these should be derivatives here, right? So this is the derivative of xi and the norm of the derivative of xi. So that expression will give us our unit tangent vector of the reparameterization, and it is equal to this expression up here, so that's x prime of f times f prime divided by this expression right here, or should I say this expression right here. So that's the norm of x prime of f times the absolute value of f prime. And let me rewrite this by breaking it up into two fractions, right? So let me get over here on the left, we'll get x prime of f times the norm of x prime of f. And then that will all be times f prime over absolute value of f prime. Okay. And now let's take a step back and sort of see what we have here. On the left, that is going to be our reparameterized unit tangent vector. That's the unit tangent vector of our reparameterization. So this piece right here, this is the, I'll just say, unit tangent vector of xi. This piece right here is really the unit tangent vector of x, right? Because no matter what I'm plugging into capital X, if it's just a t or if it's an f of t, if I'm taking its derivative, taking its velocity, and then dividing by its length, I'm getting a unit tangent vector. So this is really the unit tangent vector of capital X. And then I have this extra piece, right? This extra piece right here, f prime divided by the absolute value of f prime. And what we realize is that this expression is either +1 or -1, depending on if f prime itself was positive or negative valued. So this is either +1 or -1. And what we see is that the relationship between our two unit tangent vectors, the unit tangent vector of xi and the unit tangent vector of x, are either the same if this expression is +1, or they're pointing in the exact opposite direction if this expression is -1. And so going back to our original example here, right? If this was my x of t, and it's being traced out going in this direction, this will give us a unit tangent vector pointing in this direction. And our reparameterization xi will either give us the exact same unit tangent vector, or it will give us the opposite unit tangent vector, pointing in the opposite direction here, depending on whether our parameterization is going in the same direction as x, or if our new parameterization is going in the opposite direction as x. And that's where that +1 or -1 will come into play. All right, so before I get there, back up a second. So all of this is well and good, but we should be a little hesitant or a little skeptical of the computations we've done so far. Specifically, this is all well and good, provided that all of these derivatives and all of these divisions actually exist and make sense, right? So if our little f is not, I should say, if f is not differentiable, if f prime doesn't exist, we're in trouble. If our x isn't differentiable, if x prime doesn't exist, we're in trouble. If our speed is ever equal to 0, so we're dividing by a 0 here, or if our little f prime is ever equal to 0, we are in trouble because then we are dividing by 0. So these equations all look well and good, provided that we don't accidentally get an expression that does not exist or accidentally divide by 0. And so this will often be the case, at least in the examples we look at in this class. But I'd like to give some formal language to describe these. So first of all, I want to talk about a parameterization whose speed is never equal to 0. So our capital X is called a regular parameterization if it is C1, right? And as a reminder, C1 means that x prime, the derivative, exists and is continuous, right? So C1 means that the first derivative exists and is continuous. C2 means that the second derivative exists and is continuous, and so on. So our parameterization is regular if the first derivative exists and is continuous, and if the first derivative never equals 0, right? And notice here when I've said our x prime never equals 0, this is a vector-valued expression, so I'm saying that it never equals the 0 vector. Excuse me. And so in particular, I'm saying that x of t, y of t is never equal to the expression 0, 0. X prime of t, y prime of t is never equal to 0, 0. Okay, so regular parameterization is one in which this doesn't happen. Full disclosure, regular parameterizations, like we said, are the ones that we'll be dealing with most often in this class. And in general, this just means that nothing funky happens with our parameterization. So we talked earlier about examples in which our curve might sort of double back on itself. Well, if we have a regular parameterization, this will not be the case. This cannot happen. Similarly, right, our function, our curve, we might be worried that our curve has some sort of sharp point or a cusp or something like that that could make our x prime not exist. If our parameterization is regular, this cannot happen. So having a regular parameterization just means that our curve is nice in a lot of ways, right? It means that our parameterization is nice and the underlying curve is nice in a lot of ways. Okay, secondly, we can say that if we have a regular parameterization x and if we have a reparameterization xi, then this reparameterization is regular if that reparameterized piece, that f, does not equal 0. We can say that the reparameterization is a positive reparameterization if it's regular and if the expression f divided by, I should say f prime divided by absolute value of f prime is equal to 1. It's a negative reparameterization if that quantity f prime divided by absolute value of f prime is equal to -1. And so if our reparameterization is positive, or aka positively oriented, that means that it's tracing out the curve in the same direction as the original parameterization. So xi and x go in the same direction. If it's a negative reparameterization, it just means that they go in opposite directions. So we've spent a good bit of time talking about the unit tangent vector, and I want to conclude by talking about the unit normal vector. So given a parameterized curve, x of t, the unit normal vector, which we'll denote using a U, capital U, is simply going to be the vector that's of unit length and is perpendicular to the unit tangent vector, specifically by invoking a counterclockwise pi/2 rotation of the unit tangent vector. Now the good news is, once we've computed the unit tangent vector, this will actually be relatively straightforward to compute. So if our unit tangent vector at a given time t is given by the expression t1 comma t2, so it's some number comma some other number, then the unit normal vector will simply be negative t2 comma t1. And this gives us our nice 90-degree or our nice pi/2 rotation that we're looking for. I've also written this in its column vector form, so we can see that as well. So if our unit tangent vector is t1, t2, then our unit normal vector is negative t2, t1. Okay, so as an example, let's consider the circle of radius 5, which I'll go ahead and just draw up here. Right, so the circle of radius 5, there we go. Circle of radius 5 is going to be given by the parameterization capital X of t is 5 cosine of t, comma 5 sine of t. There are, of course, a lot of parameterizations, but this is sort of the standard one. It will be a nice big circle, sort of looks like this. Right? If we pretend that's a good circle, it sort of looks like this. Okay, so what we can do is we can compute the unit tangent vector and unit normal vector to this curve. And we'll do that as follows. First, the unit tangent vector is computed by computing x prime. Right? So x prime is going to be negative 5 sine of t. And we're going to run out of room here, so let's do that. So capital X prime is negative 5 sine of t, 5 cosine of t. Right? The speed of this, right? Well, that will be the square root of x prime dotted with itself. We can crunch those numbers, and that will turn out to be the square root of 25, which is just 5. And so our unit tangent vector t, which is just our x prime divided by the norm of x prime, right, will be 1/5 times negative 5 sine, 5 cosine of t, right? And of course we can combine this into a single expression, so written in the most simple form, we can get t equals negative sine of t, comma cosine of t. Now, if that is our unit tangent vector, then our unit normal vector will be as follows, right? From what we said before, our unit normal vector should be able to be computed by taking our expressions for t. This was our t1 comma t2. And now our unit normal vector should just become negative t2, so that's negative cosine of t, comma, and then just t1, right, this first component. So that was just negative sine of t. And in this particular example, right, kind of a cool thing to observe here, notice that this unit normal vector is actually just a negative, or I should say, a negative 1/5 of our original x of t way over here. Right, so notice how similar those are, just losing the 5 and including that negative sign. And we can see this as follows. Right, first let me give these some colors. So this color will be blue, this color will be red. Okay. So our unit tangent vector will be the vector negative sine comma cosine, and that will be the vector that's pointing forward with unit length. I should make sure this is unit length, right? So that's actually pretty small because this has radius 5. So unit length is more like this. Okay, and so on and so on. At each time t, we can compute this unit tangent vector. And then the unit normal vector will be the vector that is a 90-degree, or a pi over 2, counterclockwise rotation of the unit tangent vector. And what we see is that every single time, it's actually going to be pointing straight in towards the origin, right? Because it's the negative 1/5 of the original position vector. So if the original curve was drawn this far away, the unit normal vector now is 1/5 of that pointing back in towards the origin. And we can see that clearly in this picture.